Welcome to calculus. Fractions will pop up when you least expect it. On this episode, Stevenson will demonstrate
Let's look at another problem where we can apply our tree maps. So 19, particle motion. A particle moves along a line so that its position at any time where t starts at 0 and is greater than 0 is given by the following function. So let's make a note of that. This is position. Okay. S is measured in meters and t is measured in seconds. Okay, so we have units, so we need to be conscious of those and considerate of those when we write our answers. Now, in A, it says find the displacement during the first 5 seconds. So if it's the first 5 seconds, my interval is from 0 to 5. So displacement is basically just the position at time A minus the position at time B. So in other words, what's the position at where you ended minus what's the position at where you started? So I'm going to do, let's put our work right here. So I'm going to do S of 5 minus S of 0. And let's go ahead and put S of 5 in there and S of 0. Our displacement is 10 meters. What that means is over this 5 second interval, our particle was displaced by 10 meters. B, find the average velocity during the first 5 seconds. Okay, so again, same time interval. Let's go to our tree map. What's average velocity? Average velocity is just the average rate of change over your time interval. So we're basically going to do S of 5 minus S of 0 over 5 minus 0. Well, good news is we already figured out what this is, right? Because see how that's just displacement? That's really why, check this out, it's just displacement divided by your time, your travel time. So it's displacement divided by time. So this is 10 over 5, which is 2. Average velocity, so now be careful. The numerator was meters, the denominator is seconds, so it's meters per second. C, find the instantaneous velocity when t is 4. Okay, now we're talking derivatives here. Instantaneous velocity is just the derivative of the position function. So S prime is power rule, 2t minus 3. Now what is it at 4? So we're going to do S prime at 4. That's 2 times 4 minus 3, that is 5. Now be careful, it's instantaneous velocity. So what is my rate? It would be meters per second. D says find the acceleration of the particle when t equals 4. Okay, so acceleration, remember acceleration is the second derivative of position or the first derivative of velocity. Well, I already figured out velocity, so let's just go ahead and take that derivative. So that's 2t minus 3, so it is 2. So what's the acceleration at t equals 4? Well, it's constant, so it doesn't matter what the time is. So we can just say 2 meters per second, or you can say 2 meters per second squared. At what values of t does the particle change direction? Alright, getting into some complications. Changing directions. Changing directions happen when the velocity switches signs. So we want to figure out what are the zeros of our velocity function and then figure out when it changes signs. Alright, there's 2 ways you can do this. We can graph it or we can do it analytically. And I'm here to tell you the graph is like way easier. So check this out. Here's my velocity. What does that look like? So here it is. So I need to know what that value is. So I'm just going to take this, set it to 0, and I solve and I get 3/2. Now, this is my velocity. When does it change directions? Well, you see how velocity goes from below the axis, the x-axis, to above? That means it's changing direction at that exact moment. So at t equals 3/2 seconds, that is when it changes direction. Now, it didn't ask me to state how it changes directions. If it did, I would say, well, okay, so actually we can't because it doesn't tell us our line. It doesn't tell us if it's a vertical line or a horizontal line. So actually all I can say is that it changed directions at that point. F. Where's the particle when the position is at a minimum? All right, so there's two parts. Where, so that's an output. So where, that's position. When is that happening? At T. So we have to figure out when is S a minimum first, so when is the position at a minimum, and then plug that time in, and that'll tell me where the particle is at that point. So let's look at our position function. This is a quadratic. So let me show you how to quickly do this in your calculator. So based on this, I can do a little sketch. I know it's concave up and the y-intercept is positive. That's about it. So what I want to know, if I want to know when position is at a minimum, I want to know that point right there. So let's graph it. Now, it's a little hard to see that, so I'm going to go ahead and zoom in. So what I want is that minimum value. Do not use trace. Use the function above it, calc. So I'm going to go second, and I'm going to press the trace button to activate the calc function. And I want minimum, number 3. So it's going to ask me, hey, what's my left bound, what's my right bound? Left bound just means what's something to the left, what's your border to the left of it. So I'm going to use my arrow buttons. I'm going to move my cursor somewhere to the left. Once I'm satisfied, I'm going to press enter, and it's going to give me a marker. Now it's asking what's the right bound there. So I'm going to move my cursor to the other side now. And I can see, because that's the point I know. So as long as I'm just a little bit past it, it's fine. I'm going to press enter again. So now I can see I've trapped, or I've bordered the point I'm looking at. It's going to ask for a guess. Don't worry about it. You can, if you want, move the cursor towards it. It won't matter. Just press enter again. It's thinking. There it is. So this point is 1.5, comma 0.25, but it's negative. All right, so let's think about this. This is my position. So at about 1.5 seconds, it'll be that as the meters, okay, in the position for whatever this is. So we don't know enough context, so don't think it's like underwater or anything like that. So it's 1.5. So this is the when it's at a minimum. And well, now, where's the particle at? So we're going to take this time and we're going to plug it into our position function. So check this out. So now that we found our time at when S, or the position's a minimum, now we need to figure out, well, where's the particle at that time? Well, guess what? We don't have to put it all the way back in here. I mean, well, technically we're supposed to, but what I want to show you is how you can make your calculator do the work for you. Should you remember y equals cy1 right there? That's where the equation is. We already typed it in. So here's what's super cool. Go back to your home screen. Press the vars button right here. Now go to yvars, so use your arrow button, go over to yvars, and select function, number 1, press enter. Now you see this list? This is referring to all the function spots in y equals where you can graph functions. We're going to select y1 because that's what we used. Now, next to it, we're going to go parentheses, and we're going to put in this number that we want. 1.5, close parentheses, press enter. There's our answer. What this means is the particle is at negative 0.25 meters when the position is at a minimum.